In section 5.9, we're going to talk about radical and piecewise functions. We're going to talk about two new kinds of parent functions that we're going to graph, and then about what to do when we have multiple graphs in a function. So let's start with our key concept on page 354. It says this: radical functions, this is in the gray box, radical functions are examples of squared root functions. They are squared root functions. So a squared root function is a function containing a square root with an independent variable in the radicand. That's the square root sign. The parent square root function is y equals the square root of x. And that's what it looks like. And it gives you some examples of the t-table and so on. I will tell you this: you cannot take the square root of a negative number. So the value underneath the square root must be a positive number. At the bottom, it's important to put a bullet or underline or highlight this sentence. The domain range of the parent square root functions are all non-negative. Here's why. Your domain is what you plug in. That's your x. X cannot be negative. You cannot take the square root of a negative number. Therefore, if all you can take is the square root of a positive number, you're only going to get positives. Then it says the x and y intercepts of the parent function are both 0. It is increasing on its entire domain. It will always increase. So, we're going to go to problem 1 on page 355. Problem 1 is this. We first have to graph the function f of x equals the square root of x plus 4 minus 2. Then we have to determine the domain and range. It's going to be easy, but it's really hard to interpret this stuff. So we're going to start with the t-table. The t-table, once again, you can just get from your graphing calculator under the table function. But let's go back to what we learned a while back. We always start at 0, 0. Look back at page 354 and look at your parent function. Notice that the parent function always starts at 0, 0. So these, where I've marked the two arrows, are going to translate your parent function either left, right, up, or down. This one is going to be left or right. This is going to be up or down. Now, just like before, what's inside is going to be the opposite. So because it says plus 4, this graph is actually going to go left 4, and then it says minus 2, you're going to go down 2. So right here, if this is positive, you're going to go left that amount. If it's negative, it goes right. It's the opposite. And then what's outside the square root, minus is going to go down, positive will translate it up. So when you graph, the very first thing I want you to do, and this will make it much, much easier when you start doing this. When you graph, realize you're always going to start at 0, 0. But then you have to use these values to figure out where it's translated into. So, let's draw a graph. As you can see, the graph, I've already done it all, but let's go over it first. The first thing I did is I have to find the vertex. The vertex always starts at 0, 0. But because this says plus 4, I go left 4, down 2, minus 2, and so my dot goes here. So then I have to pick some values to the right. You can pick whatever you want, absolutely anything. So I'm just going to pick negative 3, negative 2, and negative 3, negative 2, and 0, which I plugged in up here. All I did was plug them in. For example, I plugged in negative 3, plus 4, minus 2. That gives me the square root of 1 minus 2. The square root of 1 is 1. 1 minus 2, that gives me negative 1. So all I did is just plug those in, and I get their values. Now, what's a little different here is this. Notice that the arrow does not go down. Here's why. It always starts at 0, 0 with no arrow. Because if any values to the left, for example, negative 4, any values to the left of negative 4, negative 4.2, negative 5, would make the square root negative. Therefore, that cannot happen. So, we've graphed this. That's the easy part. The hard part is interpreting the domain and range. And we haven't done this in a while, so we have to look at this. What is your domain? What is your range? It all starts with this, the vertex. My x value, remember this is your x-axis right here. So look at your x values. They stop right here. You look at, there's nothing here. There's nothing to the left. The red line stops at that point. And your x values here mean they stop at -4. So your x values have to be greater than or equal to -4. Your y values, notice this, your y value starts here and then starts going up. So your y value can't go down in this area, right here. Can't be down there. And so that means your y value, which if you look at your y-axis, right here, has to be more than -2. So your y value, your range, has to be greater than or equal to -2. So the domain is greater than or equal to -4. The range is greater than or equal to -2. Let's look at number 1 under practice A. So we're going to graph our first point, which usually starts at 0, 0, but because it goes -1 here, -1 means I go right 1, and -3 on the outside means I go down 3. So right 1, down 3. There's my vertex. So I just want to pick any values to the right of that. Now, here's where you can use your brain. You can pick any numbers you want. But for example, if I pick, let's say here, this is 1, so let's pick 2. If I pick 2, I'm going to plug that in, and I'm going to get 2 minus 1 minus 3. That's the square root of 1 minus 3. Now, you should be able to do this in your head. The square root of 1 is 1, minus 3 gives you -2. Now, that's easy. Why? Because I can take the square root of 1. 1 is a perfect square. But if I pick 3, I'm going to get 3 minus 2, which gives me the square root of 2. That's going to give me a decimal. I don't want that. So I'm going to keep going until, for example, I get the square root of 4. So what would I plug in to get the square root of 4 here? Well, what number minus 1 gives you 4? Well, that's 5. So I'm going to plug in 5. 5 minus 1 is square root of 4. The square root of 4 is 2. 2 minus 3 is -1. So I know another point would be 2, -2, and 5, -1. There you go. That's enough. Start here, and your graph's going to look something like that. So your domain and range. Your domain is what you can plug in for x. Well, what's your x value? The farthest x value right here is 1, which means nothing's to the left of that. So x has to be greater than or equal to 1. Your y starts here as well. Your y, if you look here, your y goes this way, and here's your y-axis. So your y has to go above the -3. So your range, y is greater than or equal to -3. On page 356, all you have now instead of square root is cubed root. And a cubed root function contains a cubed root with an independent variable in the radicand. The parent cubed root is shown as y equals the cubed root of x. It shows you what it looks like. Notice what happens now. There's arrows at both sides because you can take the cubed root of a negative number. A negative number times itself 3 times can either gives you a negative, or a number times itself 3 times can give you a positive. So either negative or positive work. So underneath, put a star or highlight this region. The domain and range of a parent cube function are all real numbers. They are always real numbers, all real numbers. The x and y intercepts of the parent cube root functions are both 0. It is increasing on its entire domain. Because you're increasing, you go left to right. So, let's start with the got it problem. Alright, so here's my graph. I'm going to make a t-table. So my vertex always starts at 0, 0, but there's nothing on the inside, so it's not going to go left or right. But then it says +2. So that means my whole graph is going to go up 2. So now, let's pick a number on the right and left. So I'm going to pick 1 and -1. So let's start with 1. So if I plug in the cubed root of 1, well, what number times itself 3 times gives you 1? That's 1. Plus 2, that gives me 3. What's the cubed root of negative 1? Well, what number times itself 3 times gives you negative 1? It'd be negative 1 plus 2 gives me positive 1. So 1, 3, and negative 1, 1. So this graph is going to be, you're going to get a little confused on how to graph this. It'll get better. It kind of looks like a line here, but it's going to look like this. Remember, this is your vertex. 0, 2 is your vertex. So it's going to go up this way, and then it's going to swing down and do that. It's almost like a mirrored image. So if you spun it, I mean, each little piece will kind of, like this piece right here, if you rotate it around, would be the same thing as this piece right here. So this is what's called a cubed root function. Domain and range. Your domain and range, x is all real numbers, y is all real numbers. Because your x value goes left and right, and your y value goes up and down, so it's always going to be all real numbers. All right. So now we're going to graph number 1. F of x equals 3 times the cubed root of x. There's no number underneath, and there's no number at the end, so my vertex is just going to be at 0, 0. So I'm going to pick numbers that I can take the square root of. So what numbers, the cubed root. What numbers can you take the cubed root of? Well, all I think about in my mind is this. I have picked numbers bigger than 1 and less than 1. Well, if I started with 1, what's 1 times 1 times 1? Well, that's 1. So I'm going to pick 1 and negative 1. What other numbers can I take the cubed root of? Well, what's 2 times 2 times 2? That's 8. So I can take the cubed root of 8 and negative 8. So 1. 3 times the cubed root of 1. Well, the cubed root of 1 is just 1, so that would just be 3 times 1, which is 3. Now I'm going to do 3 times the cubed root of negative 1. The cubed root of negative 1, what number times itself 3 times gives you negative 1? Is negative 1. So negative 1 times 3 is negative 3. 3 times the cubed root of 8. What number times itself 3 times gives you 8? Well, it's 2 times 2 times 2. So the cubed root of 8 is 2. 3 times 2 gives me 6. 3 times the cubed root of negative 8. The cubed root of negative 8 is negative 2. Times 3 is negative 6. So if I graph these, 1, 3, negative 1, negative 3, and 8, 6, I am out of room. It's going to be approximately, I'm going to use a blue dot, like up here, and the other one's going to be down farther. So your graph is going to look something like this. They're going to get easier the more you graph them, but they are difficult to graph when you first start. Your domain and range are both the same. They're always going to be the same for cubed root functions. The domain, x is going to be all real numbers, and y will also be the set of all real numbers. On page 357, we're going to start talking about piecewise functions. In the gray region at the top, it says this. You will learn about other kinds of radical functions in later courses. A piecewise function is a function that has different rules for different parts of the domain. Here's what that means. You basically have different equations to use for different values of x. You can graph a piecewise function by graphing each part of the equation. So I promise you this is actually not as hard as what we just did in the first and second parts of this section. All this is what I learned when I was in school, is it's like a mutant graph. You have 2 graphs in one. So you're going to use one graph for the x values up to something, and then the rest of the x values, you're going to use a different graph. So right here, it's basically saying you have 2 equations. It's saying this. You have this equation, y equals x minus 3, and you have the second equation, y equals 3x minus 2. But for every value that's 2 and less, you're using this equation. For every value that's greater than 2, I'm sorry, I got that wrong. For every value of x that's bigger or equal to 2, you're going to use this equation. Less than or equal to 2, you're going to use this one. So you're going to use different values or different equations for different values of x. So I'm going to put my graph on here. So what I'm going to do, once again, you can use your graphing calculator for t-tables, but I'm going to set up two separate t-tables. So I'm going to start with this one because it's all values less than 2. So we're going to pick 2 and numbers less than it. So I'm just going to pick 2, 1, and 0. And by the way, look at these. These are just going to be lines. These are just linear functions right here. So plug in 2. This is really easy. 3 times 2 is 6. 6 minus 2 is 4. 3 times 1 is 3. Minus 2 is 1. 3 times 0 is 0. Minus 2 is negative 2. So we graph these. So it would be 2, 4, 1, 1, and 0, negative 2. Now, there's going to be something that's going to change here. So notice, okay, this dot right here, a closed dot always means it's a solution. Do you see this right here? X is less than 2. Can x actually be 2? No. So really, this right here is going to be an open circle because that can't be a solution. So we're going to connect all these. Let me draw this a little better here. So notice that it's a line, but it's only a line up until that point. Because when we hit 2, we go to that equation. So now I'm going to plug in 2 and the numbers after 2. So the number they give you, you have to use in both. But here I use numbers less than 2. Here I use numbers more than 2. So I plug in 2. 2 minus 3, that gives me negative 1. 3 minus 3, that gives me 0. 4 minus 3, that gives me 1. So 2, negative 1. 3, 0, 4, 1. Note it, and then this is where the rest of it starts. So notice that here I put a closed dot at 2. Why did I put a closed dot at 2? Because up here it says 2 is the solution of this function. So as your x value goes along, here's our x value. X is going to be the blue line, blue line, blue line, bam, it stops at 2. Because then 2 goes to the second equation and starts here. It's like a mutant graph. It's 2 graphs in one, but they have different starting and stopping points. So in number 1, we have the first equation, f of x equals 1/2 x plus 1 when x is greater than or equal to 0. And then the second one is x minus 4 and when x is less than 0. So let's set up my 2 t-tables. And these should be really easy to graph because you've graphed lines before. These are just linear functions. So now we need to graph. So I'm going to start with values that are, when I see less than, that's the first part of the graph I'm drawing. So I'm going to look at this one. I'm going to do that in blue. So x has to be less than 0. So that means I'm going to put 0 and less than that, negative 1, negative 2. All I do is plug it in. 0 minus 4 is negative 4. Negative 1 minus 4 is negative 5. Negative 2 minus 4 is negative 6. So I'm going to graph this. So negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So 0, negative 4. Negative 1, negative 5, negative 2, negative 6. Now, did anyone notice a mistake I made? I made a mistake because it's very easy to do this. Can 0 be a solution here? Can 0 be a solution? No. So that means 0, negative 4 is actually an open circle, and I can't erase it now, but that's an open circle. So my line is going to go to the left. because that's when the x values, my domain, is less than 0. Now, once I hit 0, my numbers go up. I use the first function, 1/2 x plus 1. So 0, 1/2 of 0 plus 1, that'd just be 1. 1/2 times 1 is a half, plus 1 is 1.5. And a half of 2 is 1, plus 1 is 2. So 0, 1, 1, 1.5, and 2, 2. Your line looks like that after we hit 0. So keep in mind, this is the mistake a lot of people make, including the mistake I just made. That is an open dot because on this one, it cannot be 0. So this is your piecewise function.